This lecture is about the method of characteristics for first-order linear partial differential equations. Before we launch into that, I'm going to do a little recap on the chain rule in one dimension. I think everybody's familiar with the chain rule. Just looks like this thing here. And when we go to two dimensions, we have to think about what variables we're holding constant and the effects of changing all of the different variables that we consider. Okay, so if I have a function f of x and y, then I can write the differential of f is the partial derivative of f with respect to x at constant y with dx plus the partial of f with respect to y at constant x in variable y with a differential change in variable y. Okay, so this is sort of a general formula for expressing this idea of the chain rule, a total differential basically. But we can also consider the changes as you move along a specific path through the x and the y space. And those look something like this. So now you've got a specific variable that parameterizes that path, t in this case, that df dt. You just go through and you take how the dx and the dy change with the differential change in the dt. Okay, so that's our chain rule. And the generalization to many variable functions is rather straightforward, and we won't do much more on that, but you will see it throughout the course. So hopefully, if you need a refresher on this, you should go back and look at those things in your multivariable calculus class. Okay, so of course the obvious example for chemical engineers is the master equation for thermodynamics. You have the differential change in the energy is the temperature multiplied by a differential change in the entropy plus or minus the pressure times the differential change in the volume of the system. So these are just these partial derivatives. Derivative of the energy with respect to the entropy at constant volume is the temperature, and dE dV at constant S is the negative pressure. Okay, so if we now think about situations where we run into first-order partial differential equations, they are quite often encountered when you have a conservation law. For example, things like the continuity equation, the momentum balance equation. These are familiar in the context of transport problems. But also you have these things, as I just showed, in thermodynamics, also in statistics, and in kinetics. So think about things like polymerization or even chromatography kinds of problems. There are quite often these first-order partial differential equations to be solved. Okay, so the idea behind the method of characteristics for solving first-order partial differential equations is to convert the differential equation to an exact differential form and then to solve for the characteristics. Now that seems kind of abstract, and we will go through and show through some examples exactly what is meant by that. So this is the plug flow situation. You have a fluid flowing in on the left, a fluid flowing out on the right, and if you have some accumulation term here, that will be given by the derivative of the time derivative of u inside this plug flow region. Okay, so if you take an equation, a balance equation like this, where you've got the cross-sectional area times the velocity flowing in on the left, the value of some function u at that interface, you consider the same flow out term at a displaced interface by delta x. Here's the accumulation term, so u is what's not having a net flow here must be accounted in the accumulation within this volume. You divide by the a delta x, take the limit as delta x goes to 0, and this gives you a very familiar partial differential equation. Looks something like a continuity equation, I guess, for this quantity u. Okay, so u can stand for concentration here if you want to think of it that way. Okay, so this says the partial time derivative of u plus velocity times the partial position derivative of u is equal to 0. So we've got a balance between our accumulation and our convection terms in this equation. So that's the partial differential equation that we want to solve. You see that it's linear. It has only first-order terms, and so this method of characteristics should be able to solve this thing. And so we're going to start with an initial condition where we have u at x and time equals 0 is given. That is to say, we know the concentration everywhere along the pipe at the initial time, and it's given by this function f of x. So we know that if, for example, we start with a little pulse in concentration, that pulse in plug flow will just travel down the pipe as this traveling bump function. Okay, so we sort of already know exactly from our intuition what the plug flow solution should look like. But imagine that we didn't know, and we wanted to start with this partial differential equation and this initial condition and come up with a solution of this by just using the math and no intuition behind this thing. Okay, so let's suppose that we could do that by finding some new variables. And the new variables are going to follow changes in the initial data in something that looks like a Lagrangian reference frame. That is, we're going to imagine a set of coordinates that's going to move with the solution and follow and track its evolution as you move down this pipe. So we know that we're going to start with these two variables x and t, and we're going to need two variables in the final solution. We'll call those s and tau. And if we write that the derivative of u with respect to the variable tau is related to the partial derivatives of u with respect to t and x, then we could expand this whole thing on the left in terms of derivatives with respect to t and x as follows, right? So this is just using that two-dimensional multivariable chain rule. We've got a partial in t and a derivative of t with tau, and a partial in x with multiplied with a derivative of x in tau. And we could make this expression on the right-hand side be the sum of the two partial derivatives that appear in our partial differential equation, right? So no, why do we care about this particular combination? It's because that was the two first-order terms that appeared in our partial differential equation. So we can make this expansion of du d tau look like the term that sums all of the first-order terms in our partial differential equation if we choose the derivative of x with respect to tau to be the volume, to be the velocity, and the dt d tau to be 1, right? So basically that takes this coefficient and makes it v, and this coefficient, and it makes it 1, and we get back an equation that looks like this. Okay, so we can solve these two equations, and the solutions of those are pretty easy. They are x equals v tau plus some constant that's going to depend on s, and we don't know what that's going to be yet. And I've got this subscript bracketed x because this comes from the equation that we use to match the coefficient for the x variable. And we're going to have a similar solution for the dt d tau equals 1. That gives us that t is just tau plus some other constant that's coming from the t equation that could be varying with s. Okay, so now what we're going to do is we're going to force the new coordinates s and t to match the old coordinates x and s and tau to match the old coordinates x and t when tau is equal to 0. And because they match, that has to also mean that t has to be equal to 0 at that time. Okay? So that is to say that when we let t equal 0, tau must also be 0. And we have this constraint then that identifies the constant in s, right, for the t equation. Similarly, when t is equal to 0, we're going to require these two coordinate systems coincide, and that says that x has to be equal to s. And so that gives you the s at tau equals 0 should be 0. Let's see why that is. So s should be equal to 0 plus the constant in x times s, right? So this is that thing translated. So this comes from this equation. And so we see that this constant in x must just be equal to s. So we can replace this thing up here with s, and we can replace this with 0, and that gives these equations. Okay? So now you have that x is equal to v times tau plus s, and t is equal to tau. And you can invert that coordinate transformation and get that tau is equal to t. That one was pretty easy. And that s is equal to x minus vt. Okay, so now we've expressed the new coordinates t and tau and s entirely in terms of the old coordinates t and x. All right, so why did we do all this? Because it groups those first order terms in our partial differential equation into one term. Okay, so our partial differential equation was this guy, and now it's just du d tau equals to 0. Okay, so the right-hand side remains 0, but the left-hand side has been replaced by this total derivative of u with respect to tau. Okay, so now we can solve this problem in the tau s coordinates. It's pretty easy. We have that u cannot depend on tau, and so u must just be some constant that depends on s only. Okay, so we have that u of s and tau is equal to u of s and 0. Remembers that initial value along tau forever, and that's why we call these things the characteristic coordinates, is because it's remembering the initial condition as you move along the new coordinate system, along the new coordinate tau. Okay, so here is f of s, and this is our solution in the s and tau space. We have solved this problem. So in order to so note, we did this matching of the s and x coordinate system so that we could insert at when tau is equal to 0, I know that x is also equal to s. Okay, so that says I can just take u of s and 0 and equate it to f of s, where, you know, originally I had an x here, but when tau is 0, this is true. Okay, so now we can quite easily recover our solution in the x and t space. It's just this thing with the s replaced by its equivalent mapping back to the x and t coordinate system. Okay, so indeed we find that this plug flow equation gives rise to traveling bump solutions. Whatever goes into the reactor at the initial time just moves with some characteristic velocity down the pipe. Okay, so in general, if you have a first order linear partial differential equation with complicated coefficients, a of x and t and b of x and t on the convection term and the accumulation term, if you want to think of them that way, then you can define a generalized velocity that's a function of x and t given like this, and that basically makes this problem look exactly like the problem that we just solved above. So you know, in the general case, you get these curvy relationship between s and tau and x and t. Okay, so but you will still see the initial information tracked through space along the new coordinates s and tau. So it's sort of the initial information is being propagated, and you look along the s coordinates to see where you are related to your initial data, and you look along the tau coordinates to see how that's moving through the system. Okay, so the plug flow case is just a special situation where the velocity in this ratio is a constant. Okay, so that's basically the idea behind the method of characteristics. Of course, as you can imagine, problems get a lot more complicated than our simple plug flow equation. Let's consider a slightly more complicated example where instead of having 0, so in the plug flow case, we just had something that looked like this. Not only that, we only had t and x. Here we're going to introduce a y coordinate as well. So we've got a 2 spatial dimensions and 1 time dimension. And we also have that these first order partial derivatives, linear combination of partial derivatives, don't add to 0. They add to k times u. Okay, so the solutions will look a little bit different now because of this. Our initial condition now has this form. It's u of 0, x and y is some function of x and y. And again, this problem would be very easy to solve if we could collapse all of these, first order partial derivative terms into one term du d tau. Okay? So if we could collapse all of that into this one guy, we would have this simple equation and we would be able to solve that thing immediately. Okay, so how do we do that? Well, we go back and we use the chain rule. So the derivative of u with respect to tau is the partial derivative of u with respect to time, d time d tau plus partial of u with respect to x, dx d tau plus partial of u with respect to y, dy d tau. And this, so this equation would look exactly like the first order partial derivatives that appear in our PDE, that is this group of terms, if we were to choose that the dt d tau is equal to 1 and dx d tau is equal to v, and dy d tau is equal to v. Okay, so let's see that. If we make this guy v, and this guy v, and this guy 1, then the thing on the right-hand side is exactly what appears in the partial differential equation for the first order terms. Okay, so we can go back and we can introduce new coordinates. The new coordinates are tau, q, and p, and those should coincide at tau equals 0 and t equals 0 with x and y. Okay, so this is the transformation that we envision. We want to find that t, x, and y can be expressed in terms of tau, q, and p, and then hopefully we can invert that and find tau, q, and p in terms of t, x, and y. We do that by solving these three equations. So we set these, we chose these coefficients, the 1, v, and v, for the time x and y derivatives with respect to tau. And when we go through and we solve those, remember that t is going to be equal to tau plus some constant that depends on q and p. Likewise, x is going to be velocity times tau with another constant that depends on q and p, and y as an equation that's very similar to x. Okay, so now is the interesting part. We now force the old variables to coincide with the new variables on the specific part of the surface where t is equal to tau is equal to 0. So that is to say, when we consider the initial data, I want the x and the y to coincide with the q and the p. Okay, so that now specifies those undetermined constants after the integration step. So we want tau at t at tau equals 0 should be just equal to 0. That is to say, it's the same as tau. And that gives me t equals tau over here. We have that x at tau equals 0 should be the same as q. And that says that this undetermined constant should actually be q. And so that gives me a mapping from x to x from tau and q. And y should coincide with p at the initial time. And that gives me that this constant should just be equal to p, which tells me that p plus v tau should be y. Okay, so that was easy. Okay, that was really easy. And often these problems with constant coefficients are quite easy. Okay, so now we have du d tau plus ku is equal to 0. And this is our partial differential equation, right? It doesn't look like a partial differential equation anymore, but it's still all the same content. By construction, we made this true. And so we can easily solve this thing now. It says that u is just equal to u at the initial time tau with an exponential decay e to the minus k times this tau. Okay, so that is the solution in the tau qp space, where we would just need to know what is this thing as a function of the q and the p. Okay, so it's only this u of t and 0 part of the solution that can actually depend on the q and p, and we're going to use the initial data, the initial conditions, to get a specific version of what that u of tau 0 is. Okay, so it's u of 0, q, and p. Remember that t and tau coincide here, and so that says that this guy is exactly the same as u of t equals 0, x, and y. X and y are the same as q and p at the initial time, and so we just replace this by f of q and p. So it's because we matched the coordinate systems that we're able to do this last step. Okay, so hopefully you guys really think about this carefully, and remember that this is sort of the guide of what should match what. You look at what kind of initial data that you have, and you want to be able to do this at the end of the problem, and so that's really how you choose which coordinates to make into which other coordinates. Okay, so now the last step is to take this solution and convert it back to the x, y, and t space, and that's rather trivial to do because we have our mapping from q and p to x, y, and t, and that gives us a solution that looks like this. Okay, so now u of x, y, and t is just f of qp, but it's q and p are x minus vt and y minus vt, and we have our exponential decay. Okay, so this is giving you damped surface wave solutions, And you know, if you look back in the original equation, that is, I guess, what we should expect, right? This is a damping term, and we have something that looks like waves here in the two convection terms in this problem. Okay, so that is a method of characteristics problem. We will do. We will go ahead now and do a more complicated example and consider this problem from the final exam back in 2010. Okay, so this problem we consider a species. Let me go ahead and break the video and start this one in a fresh one.